Hi everyone. Today we're going to begin talking about systems of equations, what they mean, and how we solve them. So let's use this as an example. What you have is a system of equations, and basically that means two equations, two linear equations, and our task is to find out where they intersect. Another way of putting that is find the x and y values which make both equations true. So let's write that down. We'll have two ways of solving a system of equations. The first way is to simply graph the two of them and try to see where they intersect. And you should understand that the only time in which you won't have a solution is if the two lines are parallel. The problem with the graphing solution is that you might not always have a nice, easy point that you can tell. For example, if the solution was 1/2, 2/3, it would be very hard to tell that by using two graphs of the lines. So we'll look at the graphing solutions in this section, but in the next two sections we'll look how to solve exactly using algebraic analytic techniques. One of the things we can do is it's a little contrived, but we can say, okay, we're going to tell you that 2 comma minus 1 is a solution to this and show it. In other words, check that that's the solution. So what we do in that case is simply plug in 2 for x and minus 1 for y. So we have 2 times 2 minus 3 times minus 1 equals 7. And if we simplify that, we get 4 plus 3 equals 7, and yes indeed, 4 plus 3 does equal 7. If we check in the second equation, we have 2 plus minus 1 equals 1. That's the same as saying 2 minus 1 equals 1, and of course that's true. So this is just a way to check that 2 comma minus 1 is indeed a solution to this system of equations. So let's use this as an example. We want to solve this system by graphing. Y equals minus 1/2 x plus 3, y equals 3/4 x minus 2. Now we could do this on a piece of graph paper, but I chose to use a graphing utility to show you how that might be able to be used. Let's see if I can bring that picture in. So here I've used a graphing utility to show these two graphs. Here's the graph of the first, and here's the graph of the second. And if we look real close, and if this weren't quite so shrunk up, we could see that that solution is 4 comma 1. And again, if that solution happened to be 4.5 comma 1.86, there's no way that we could guess it by graphing. And all you might want to do at this point is check that that solution is correct. We'll check in the first one, and you can check in the second one if you'd like. So in the first equation, I'm going to put in 1 for y, and does that equal minus 1/2 times 4 plus 3? That's the same as saying, does 1 equal minus 2 plus 3? And yes, indeed, it does work. So you can check the other solutions, but you can take my word for it, that is going to be correct. I want to point out that what is nice about this particular system is both equations are written in slope-intercept form. So it's very easy to just simply graph them using the y-intercept and the slope. In the next example, you'll see where that isn't quite so nice. So let's look at this problem. Here we have equations that are written in standard form. And if we wanted to graph them, we would want to put them into slope-intercept form. In other words, solve each of them for y. What is a more clever way of doing this is what's known as the Coverup method. The Coverup method gives you a really quick way to find both the x and the y-intercept when we are given an equation in standard form. Now remember, the y-intercept is where x is 0, and the x-intercept is where y is 0. So if we want to know what the y-intercept is, we cover up x and basically cover it with your finger, with your hand, and just let it be 0, and then solve minus 3y equals 8. To find the x-intercept, we cover up the term involving y, and we solve for x. And we would get 4 in that case. And then since we have 2 points, the x and the y-intercept, it's easy enough to graph them. So let me show you what I mean here. So for the first equation, what we're going to do is, to find the x-intercept, we cover up y, and we let y equal 0, in other words, and we solve for x. And if we do that, we see we get x is equal to 4. For the y-intercept, we cover up x, and we see the y-intercept is minus 8/3. In the second equation, the x-intercept, we cover up the y, and we get x is equal to 2/3. For the y-intercept, we cover up the x, and we see that the y-intercept is minus 1. And now all we need to do is graph these two, using those 2 pieces of information for each, and hope that we can guess where the 2 lines intersect. So you can see here that I made this graph freehand, and try as I may, it still wasn't as nice as it should be. One of the things that I do know in advance is what the solution is, and the solution is minus 2 minus 4. And if I had made a really nice graph, or if I had used a graphing utility, it probably would have shown up a lot better. But right here is the place where those 2 lines should have intersected. So close, but not very good. So if nothing else, what you should understand from this is that although the graphing method does give you an idea of what we're trying to do, which is find where 2 lines intersect, or the solution to both lines, it's not the most effective way. So we need a better way, and that's coming up in the next section.